I'm very excited to share with you our work on sign language generation, which we recently presented at CVPR 2026. The title of our paper is Focal General Diffusion Model with Semantic Consistent Guidance for Sign Language Production. First, let me introduce what sign language production is. The goal of sign language production is to convert natural language into sign language motion sequences. These sign sequences can take various forms, such as sign language avatars, RGB videos, or skeletal representations. Among them, generating sign language videos directly is very challenging, as it requires prior information from already generated skeletons and avatar parameters. The frameworks for generating avatars and skeletons are generally similar. In this work, we focus specifically on the task of skeleton generation. Generating sign language sequences directly from natural language is inherently difficult because the grammatical structure of sign language differs significantly from that of spoken language. To bridge this gap, we introduce glosses as an intermediate representation. A gloss is a word-level annotation that follows the grammar of sign language. In practice, the model first converts natural language into glosses and then translates these glosses into sign language sequences. Existing research has mainly focused on this second step, commonly referred to as gloss to sign. We summarize the contributions of our paper in 4 main points. 1. Focal General Diffusion Framework. We propose a 2-stage denoising network with focal and general stages. The focal stage focuses on local details such as joint dependencies, while the general stage captures global information. 2. Adaptive Semantic GCN ASGCN. In the focal stage, we design a novel GCN. Since sign language sequences lack explicit semantic boundaries, ASGCN models each frame individually, adaptively adjusts the adjacency matrix based on contextual correlations, and injects semantic information through a semantic mask. 3. Semantic Consistent Guidance, SCG. We introduce semantic supervision during diffusion training, ensuring that the generated sign sequences are highly semantically consistent. Key Tyree, state-of-the-art performance. Our method achieves state-of-the-art results on the widely used German dataset Phoenix 14T, and also sets new records on the Chinese dataset USTC-CSL. This is the overall framework of our paper. During training, we use DDPM to add random noise to the target sequence, generating a noisy sequence. This noisy sequence is then fed into our 2-stage denoising model, which denoises it conditioned on the gloss. The model is supervised by the standard coordinate regression loss as well as our proposed SCG loss. During inference, we use DDIM to iteratively denoise and obtain the final predicted sequence. In tables 1 and 2, we report backtranslation results for FGDM. Backtranslation means feeding the generated sign sequences into a pre-trained sign language recognition or translation model and evaluating them with various metrics. Here, blue and rouge measure translation quality, Weyer measures recognition accuracy, and FID evaluates feature space similarity. As we can see, our method outperforms existing models across all metrics on both datasets. An interesting observation is that FGDM even achieves a lower WER than the ground truth. We believe this is because FGDM fits the training data distribution so well that the back translation model can recognize the generated sequences more accurately. Considering that existing metrics may not fully reflect model quality, we conducted a user study. In this study, participants were asked to vote on anonymously generated sign language videos, judging which ones were closer to the ground truth. As shown, FGDM received 80% of the votes, demonstrating a clear advantage over existing methods. The table on the left records all the voting results. This is our code and project homepage. Feel free to visit for more details. For further information, you can also refer to our paper. That concludes my presentation.